Hey guys, today we're going to do a little video lesson on partial fraction decomposition. This idea has a couple of special cases, and while we can't appreciate all of its applications right now, we'll definitely be able to see a lot of the reasons why this method might be useful once we get further into our studies of calculus. So for now, the goal of partial fraction decomposition is that we're going to want to separate functions of x currently represented as rational functions, and we want to represent those in terms of a linear combination of simpler factors. So the idea is that let's assume that we're starting off with a function f of x equals p of x over q of x. The goal is that we want to express this in simpler terms where we decompose the denominator q of x. What this would look like is this might be, let's call this a1 of x over b1 of x plus a2 of x over b2 of x up to whatever number of terms we might need. Let's say plus a sub n of x over b sub n of x. This notation in particular means that the product of all of these b functions will give us back q of x, the denominator, and each of our a sub i's, each of our a of x functions, are simply functions of x. They might be constants, they might be more complicated than that, but generally one thing we can safely assume with the scope of what we're looking at and where this method really shines is where all functions other than f of x are polynomials. So p of x, q of x, all the ai's, all the bi's, those are all going to be polynomials. So this is going to break down into kind of three general cases. Let's say case one is where the numerator is constant and the denominator is easily factorable. Let's do something nice and easy, like our example is f of x equals 3 over x squared minus 1. There are, of course, going to be domain restrictions, but that's not the scope of what we're concerned with at the moment. We want to know, how can I split this up? The strategy is we are going to factor the denominator and choose those factors as the denominators of our linear combination. So x squared minus 1 factors into x plus 1, x minus 1, because it's a difference of squares. So this means that f of x is equivalently 3 over x plus 1 times x minus 1. And what I'm going to claim, because the factor in the numerator is a constant, that means I want to express this as a string of constant values. I'm going to assume that there are some constants a and b such that we can split this into a over x plus 1 over plus b over x minus 1. So in order to accomplish this, I'm just going to bring these back together using a little bit of algebra. I started with one fraction, I have two, but in order to solve for a and b and create a system of equations, I'm going to bring these together into one fraction. And we can do that by getting a common denominator. So I'll multiply this by x plus 1. I'll multiply this by x minus 1. And now all the numerators are the same, denominators are the same, so we can compare the numerators. So the denominators are all equal now because we have a common denominator, and now I can just look at how the numerators will all expand. So this would be 3 is equal to a times x minus 1, which is ax minus a, plus b times x plus 1, so bx plus b. We can create our system of equations based on the following facts, that if two polynomials are equivalent, all their corresponding coefficients have to be equivalent. So because I don't have any x terms on the left-hand side, that means the sum of ax and bx have to add to 0x. So that means a plus b has to equal 0. Because our constants are negative a and positive b, that means negative a plus b has to give us our constant on the left-hand side, which is 3. So this means that b minus a is equal to 3. Well, okay, I'm just going to add this straight down. We'll just treat this like a system. So if I add these straight down, then we're going to get that the a's cancel out. So 2b equals 3, which means b is 3/2. And by that logic, a plus b is 0. So that means that a is just going to be negative 3/2. And so this means we can successfully decompose 3 over x squared minus 1 into negative 3/2 over x plus 1 plus 3/2 over x minus 1. And that would be our partial fraction decomposition. That's nice and easy. Let's look at another case. I'll call this case 1b, where we still have the same condition in the denominator. It's still going to be an easily factorable polynomial, but the numerator is a more complicated function of x. The previous one, a constant, is technically a function of x, but this will be a little bit more of an interesting one. Let's say I want to decompose 2x plus 1 over x squared plus 5x plus 6. So we'll start the same way. We can say that x squared plus 5x plus 6 decomposes into x plus 3 times x plus 2. So that means the denominators I'm choosing here will just be x plus 3 and x plus 2. Now, because the denominators are linear factors, I'm still going to assume that the numerators are constants. The general rule that we're going to follow is that because I can split each of these into linear factors, or whatever degree they might be, the numerator will be 1 degree less. And that's a useful idea to keep in mind. So we'll assume, again, there are constants a and b that satisfy this. The worst thing that could happen is there aren't, and when we try to solve this system, we get a contradiction. So I'll do the same thing. I'll multiply this by x plus 2. This will be times x plus 3. And now that we have a common denominator, I could just compare across the numerators. So this would be saying 2x plus 1 equals ax plus 2a plus bx plus 3b. We'll pair the x's, we'll pair the constants. So this means ax plus bx has to equal 2x. So that means a plus b equals 2. The second equation in our system is that 2a plus 3b has to equal 1. 2a plus 3b equals 1. Now we'll just solve this like a system. I'll choose, we did elimination last time, I'll do substitution this time. I'm going to substitute that a equals 2 minus b into this equation. So that'll give us 2 times 2 minus b plus 3b equals 1. So 4 minus 2b plus 3b equals 1. So 4 plus b equals 1, which means that b is negative 3. Because a is 2 minus b, that means a is 2 minus negative 3, which is 5. So looking at our original question again, this just means, in summary, that 2x plus 1 over x squared plus 5x plus 6 equals, a was 5, so 5 over x plus 3 plus negative 3 over x plus 2. And that would be our valid partial fraction decomposition. Let's look at the second sort of interesting case, and this is just going to be where the denominator doesn't easily factor. We're going to end up getting stuck at a point. We'll see what we mean. So this is going to be the case where the denominator is not easily factorable. So let's see. Let's say that I want to find the partial fraction decomposition of 3 over x minus 1 times x squared plus 1. Okay, we have a linear factor, so I can just pull that out. Definitely one of my decompositions is going to involve x minus 1. But x squared plus 1 doesn't factor over the real numbers. That has complex solutions. When that happens, this means that we're going to leave it uninterrupted. That has to be the second factor. The numerators, in this case, once we've reached an irreducible polynomial in the denominator, when it can't be reduced anymore, that means that we're going to assume the terms in the numerators are 1 degree less. This will just be a constant because 1 degree less than a linear equation is a 0 degree, which is a constant. The second one, 1 degree less than a quadratic that's irreducible, is a linear term. So we're going to assume this is bx plus c. Logically, we have to assume that because we're going to need to think of a way to then introduce some sort of quadratic into this so that we can help to compensate for the fact that this term can't reduce. Otherwise, it's the same thing. We're going to multiply this by x squared plus 1. This will be multiplied by x minus 1. So from here, it's just business as usual. This will be 3 equals ax squared plus a plus, now here we just have to FOIL, bx squared minus bx plus cx minus c. We're going to pair everything as we normally would. We're going to compare the corresponding coefficients. We don't have any x squared terms. I have ax squared and bx squared. Those must sum to 0. So a plus b has to be 0. We don't have any x terms, so negative bx plus cx has to be 0x. So c minus b has to equal 0. And we have two constants, a and negative c. Those have to equal our other constant. So a minus c is going to equal 3. We'll notice we have 3 equations with 3 unknowns. This is going to be pretty easy to solve. I'm just going to take the first 2 and collapse them by adding straight down. That'll get rid of the b terms. So a plus c equals 0. And we have a minus c equals 3. And then I'm going to solve those by elimination. That gives us 2a equals 3. So a is 3 over 2. Okay, well, this means that if a is 3 over 2 and a plus c is 0, that c must be negative 3 over 2. And if c minus b is 0, that means negative 3 over 2 minus b is 0. So b is going to have to be negative 3 over 2, because negative 3 over 2 minus negative 3 over 2 is equal to negative 3 over 2 plus 3 over 2, which is 0. So that tells us it felt like we maybe encountered a problem originally, but we solved it easily. This gives us that our original expression, 3 over x minus 1 times x squared plus 1, does have a partial fraction decomposition. It ends up being, in this case, 3 halves over x minus 1 plus negative 3 halves x minus 3 halves over x squared plus 1. And that's really all there is to it. So if it can factor, break it down into all of its linear terms and express those as separate fractions and solve your system of equations. If it can't break down, if it's an irreducible quadratic, all that means is assume that the term above in the numerator is 1 degree less, and then just proceed as usual. Hopefully this method makes sense. If there is anything that's confusing, please feel free to reach out and contact me. Otherwise, I look forward to hearing from you all soon.